Hello everyone. In the comments to a recent video on improvements to the Asuka spaceplane, which we have here, there were questions about the landing gear placement as well as the tank placement in the vehicle. So we see that the front landing gear is fairly far back, and that is because this spaceplane was based on a scramjet, and the scramjet has a really big intake here. And as a result, the forward nose portion is very high off the ground, and it would be really awkward to place a nose landing gear from up there. So we basically have to put it at the bottom of the scramjet, which places it pretty close to the main landing gear. And we have to make sure that the center of mass is closer to the main landing gear than the nose gear. It is still a sort of tip forward risk, but as long as the pilots are gentle with it or the program is gentle with it, it should be able to nose down safely, as I've done in Kerbal Space Program when I've used this. But how do I know that the center of mass isn't in the wrong location? With respect to the landing gear, with respect to the fuel tanks, with respect to the wings, because they have to be at the right location. Their center of pressure has to be just behind the center of mass. In a bigger airplane, in an airliner, you would expect that the wings would have the fuel in, and the reason they have a fuel in is because they are close to the center of mass, and so putting the fuel in them not only strengthens them, it's better for structural reasons, but it also means that as the fuel depletes, the center of mass doesn't change. But then also we have the additional issue of the landing engines for this space plane, because it can land on the moon or Mars horizontally using these. And these have to be centered at the center of mass too. So we expect the center of mass to be here. But how do we know that? Of course, we could turn off two of them and then keep it balanced, and that is part of the intention. There's going to be some thrust control over that. But how do we know what the center of mass is when this is so complicated? First of all, I designed it with one principle in mind, and that's that the cockpit, the additional mass of the crew accommodations, was going to counterbalance the engines. And to some extent, it's also a structure around the cockpit, including the windows. The engines are very heavy. They're 6 tons. And actually, the cabin itself is not that heavy. Cabin plus windows is still not that heavy, but there's a lot of structure around it over here. So there's that principle. And then we lay out a lot of the rest of the stuff so that it's centered around the intended center mass back here. And we also array the tanks inside like that. So if we see the tanks, the other question was, why is the methane tank here? And why don't we just have one big hydrogen tank instead of 2 hydrogen tanks? We have 2 hydrogen tanks like that. Well, part of the reason that we have 2 hydrogen tanks is because if we have one big hydrogen tank, it's weaker. It's lighter that way because we skip these bulkhead, I'll call them bulkheads. This portion and that portion, these walls, we don't need if we have one hydrogen tank. And we could split the methane tank so that it's one over here and one on the opposite side, so it's still centered on the center of mass. But mainly it's structural reasons that we have 2 hydrogen tanks, so that they're stronger. And if they've got this extra wall, then we don't have to put as much internal structure. If it was a long hydrogen tank, we would have to put more internal structure to support it. And already they have to be thicker than I originally expected them to be. So I've thickened them up and taken some of the margin that I originally planned for in this. So I had sneakily added some margin here and there, and I've decided to use that margin in order to make these thicker and do some other things. But anyway, it is still basically centered on the center of mass. So that's the basic idea going on here. What is going on with this? Oh, I think its mirror object is wrong. Let me just... There we go. Fix that up. Because I'd moved things around to show the center of mass thing. I have made the grid, when I say move it around, originally the 0 point was in the cockpit for Kerbal Space Program purposes. That's not the center of mass. Because the 0 point was at the cockpit, I had to tell Kerbal Space Program to move the center of mass back. But again, we go to the question, how do I know what our center of mass is? But the first thing we would like to do, it's okay to have part of the vehicle in negative, in other words, have some of it on one side of the axis and some of it on the other side, so that some numbers are negative. Technically, that won't change the calculations, but it's just nicer to have it all on one side of the axis so that we can just pretend that the very point of the nose is 0, and then we just calculate the numbers positively the rest of the way. Technically, it's negatively as far as Blender is concerned, but I'm just gonna make it positive. And so we don't make any sign errors for where the location of things are. So in Blender, we can take any given part, go to Object, and set Origin to Center of Mass Surface. So then it will tell you where the center of mass is based on the surface area, as long as what you're selecting has a relatively even density, if you will, or a relatively even amount of mass based on the surface area, then you can do that. It's better not to do it with like the landing gear, which has a lot of finicky bits, and so we're not going to want to calculate that. Calculate it like that. We'll just calculate it visually, basically, and otherwise it's fairly consistent. For the wings, you'll end up noting that I don't have it like that because the wings come in multiple parts, including the elevons, and the actuators and hydraulics for the control surfaces tends to move the center of mass a little bit further back, and so same for the rudder on the vertical stabilizer. So we don't necessarily want to do it for those anyway. So in my spreadsheet, I have a rough estimate for where the center of mass is for the aerodynamic surfaces. So that's how it is for that. But otherwise, you can just go with the center of mass by having it here. But besides the center of mass, we have to know the masses of each of these objects. So you have to figure that out. And you know, this is all above and beyond normal Kerbal Space Program things. Trying to get it to show that again. But if you're going to make a model of something like this and you really want to be honest about it, you have to figure out how much everything weighs and then figure out the center of mass. For a capsule, you know, you can just use the surface area and it's very simple. And the main reason I'm doing this is because in Kerbal Space Program, the whole body is one part, right? So basically, this whole thing up here is a single part in Kerbal. Now I've got a lot of wires hanging out. But yeah, that's all one thing in Kerbal Space Program. So then how do I figure out where the center mass is? I have to be honest about it. So we have to go to a spreadsheet. And I'll show you how to lay that out. So we have our parts and we have their masses. So we have one column for the masses and a column for the masses. Anyway, no, and then we have the center mass locations that we found in Blender. We take the masses and we multiply by the center of mass location to get a resultant. And so we have all these numbers that technically don't mean anything, except they're the magnitude away from 0 that each of these masses is. So then we have all of these, and we can calculate the center of mass based on summing up all of the resultants. So add all these resultants up, and then divide by the mass. So we had the masses times the center of mass. We multiply each of them together. We get this resultant. And then we divide out the mass again, and the result is the center of mass. So if you want to think about units, we've got kilograms, we've got meters, and then we've got kilogram meters as the resultant. And then we divide out the kilograms, we end up with meters. So for the base model, this is the total mass as we sum up the pre-calculated equipment up here, plus the structural mass here. That's what goes into here. It's F14 plus F85. So it's this mass here. So that's the total for the base model. And we take the sum of all the resultants from the base model. So up here, So from I3 to I43, up till that point, all of these numbers, we sum them up, and then we divide by this. And that gives us the center of mass of the base model. And it is at 37.37. Then we take the optional additions, which happen to be all arrayed very close to the center of mass, for reasons. And we're omitting the jet ramjets, the pit unit there, and we don't need the canards, generally speaking, for interplanetary operations or landing on Earth. We just need it for taking off, so that would be for taking off. And the Asuka spaceplane in this configuration cannot take off. It can only land. So we have these additional masses and their resultants. And so now this one adds more resultants and then divides by this increased mass, which is increased by that amount from the interplanetary options here. And then we get 37.38, which gives you an idea how closely I've made all these things. So all the optional doodads don't move it more than 1 centimeter. It moves it 1 centimeter. Okay, so we've got all that, but we do have this cargo bay up front. Let's take a look at the plane. Right? You might have noticed that there's a cargo bay here, and that can have a variable mass. There could be different things in there that change the center of mass. And we might be keeping that coming back down. Going up is not a big deal. Let's get rid of the boosters and the jets. Going down is the issue. If we're carrying it back down, this all needs to be balanced. And that could be down to the lunar surface, down to the Martian surface, or down to the surface of the Earth using the wings. So it's a matter of using these engines or using the wings. We need it all balanced. So how far forward does the payload in here move the center mass? Now, my intention is not for it to carry a really heavy payload in the cargo bay. In fact, the ramp, I think I've decided that it should only be able to carry 4 tons when being deployed like this. So that's the limit of the ramp, though more can be slapped into the bay, tied to the sides and stuff like that. But nominally speaking, it could potentially carry 10 tons, and we've tested it up to maybe 12 tons, I think it was, during the testing. So it could carry that much. So let's see how we set that up in the spreadsheet. So I've got this cargo bay mass, and so that's another mass here. And the center of the cargo bay is at 22 meters. So we're just going to assume that that's where we're going to be putting the payload. And so we get our resultant there. And now this number sums not just what we had before, but all of that plus this. And then we divide by this number, which is the normal configuration dry mass plus the cargo bay mass. And what we see is that it does move the center of mass forward a bit, but it's by less than a meter. And if we increase this to 8 tons, well, now it's more than a meter. It's about 1.4 meters forward. So it's actually more of a problem for the center of lift than really the landing gear. If we take a look at the locations of all this, so let's say we're at 36 with 8,000, or if we wanted 12,000 kilograms, now we're all the way at 35.36. So that's pretty far forward, and we wouldn't want to come down with that. What I would say is we can come down with 4,000 maybe. If we take a look at how the plane is set up, where is this anyway? Where are these numbers? Well, let's take a look from the bottom end. So that's 0, 10, 20, 30, 37.7-ish is back here. You can sort of see this is the 37 line. And then so the empty, it was 37.37. So the center mass when the whole thing is empty is here. And then when you add cargo, it was at 36, right? So it's here. And then if we add 12 tons of cargo, it's at 35.3. So that's basically here. So that's 30, 31, 32, 33, 34, 35.3. So somewhere around here. So it's certainly still well behind the nose gear, though we don't want it even close to the nose gear, really. But It's also not so far back that the thing is going to flop on its tail based on where the main landing gear is. So we've got that going for us as well. And certainly when you take a look at where the wing is, the center of lift will be pretty far back compared to the center of mass too. So we've got that as well. Other than that, well, there is the matter of what happens when it's fueled. So is our fuel configuration in the right location? Well, I think we've settled that the landing gear isn't a huge problem. So let's hide the body and the ISRU unit again. So these are our fuel tanks, right? And we've established that the empty center of mass is around 37.37, so here, where my cursor is right now. In fact, we can set the cursor from Blender at that location. This 30, I could actually type it in if we want that as a reference. Okay, yep, 37.37 or 38 if we've got all the doodads. So that's the center of mass. If we take a look at the tank configuration though, the center of mass is almost certainly going to be the going with the center of the liquid oxygen tank, which is what we have here, because the liquid oxygen is much, much heavier than the hydrogen or the methane. And so that's going to drag the center of mass back a bit. And we expect the furthest rear that the center of mass is going to go is here. So I'm not going to add it to the spreadsheet, the fuel thing. This is as far back as we would expect it to go, so to 39. And so as long as there's some fuel in here, it will drag it back. And then, you know, if you put some cargo in, it probably still results in it being around 30. Well, if you have a little bit of fuel and you have a little bit of cargo, ultimately is going to settle back to where the center of mass is here, 37.37 or so. So that is how it all shakes up. And no, the methane tank is a little bit forward of it, but it doesn't make too much of a difference. You can see all the center of mass options for this range around here, which is actually a wider range than the space shuttle would have. But operationally, as we see in Kerbal Space Program, it doesn't throw it off. In other words, it seems pretty well balanced, even though we have it like that. Good. So it's working out. The center mass is there in Kerbal Space Program. The wings are as they are, and FAR seems to like that just well. And when we land on the moon or Mars, it manages it. So we've got all that, and that is how to calculate your center of mass. You're gonna need a spreadsheet if it's this complicated. If it's not this complicated, let's say you've just got a pod and you figure the internals are going to go along with where the surface area is. You know, you just got a cone, you just go set origin to center mass surface, figure it out like that, and call it a day. You don't need the spreadsheet if it's something that's really simple and you're not dealing with landing engines and wings and stuff like that. If you're dealing with landing engines and wings, maybe you should do it a little bit more carefully. And if you have it all broken down in Kerbal Space Program so that the tanks are separate from the body or the cockpit, you know, you have one cockpit and then the tanks are separate and the engines are separate. Well, here the engines are separate. But if you've got things broken up like that, like the normal Lego system that we have in Kerbal Space Program, then let Kerbal handle the center of mass and you're okay. So it's only really with one of these complicated vehicles where we're bundling a whole lot of things in, how do we know that it's really where it ought to be? And ultimately it comes down to a spreadsheet, which, you know, I've critiqued spreadsheets before, but spreadsheets are fine for static things. I just don't like them for dynamic things like launches. People who use spreadsheets to decide whether something can actually lift a certain payload, that worries me, because they're usually forgetting about thrust weight ratio, effects, gravity losses, drag, stuff like that. So, all right, so with that, thank you for watching. I hope you enjoyed this video. If you did, please do press like. If you have any comments or suggestions, please leave them in the comment section below, and I'll see you next time.